So I'm trying some Beluga now. I wanted to try it out, so I finally did, and I just wanted to type it down somewhere so that I will remember it if I ever need it later on. So let's do some hello world kind of stuff in Beluga. So Beluga's file extension is BEL, and that's what they usually use, and it has an Emacs interface, which is what I'm using at the moment. Alright, let us get started anyway. So first, the usual stuff with natural numbers. So first we declare that the natural numbers, this is the name that we are using for natural numbers, the type of natural numbers. We are saying that nat is a type. Okay, now I will just compile this. In this Emacs interface of Beluga, we can do Control-C, Control-C to compile the file. So that's what I'm going to do now. Control-C, Control-C. Ask me what command to run, and it has run. Okay, so far so good. Right now we say what all values are part of nat. So nat is a type, so now we need to have ways to make values of that type. So there are two constructors, 0. These are names that I myself am giving. You can give different names if you like. So I'm saying 0 is a natural number, and I have a successor such that given a natural number, I can give yet another natural number. The idea is that successor of a natural number is 1 plus that natural number. Okay, let's compile again. So the comments start with a percentage sign. Alright, I compiled again. Yeah, it worked. Okay, now we have our definitions, alright. Let us make a function. Okay, I won't be doing any proofs in this. Proofs in the usual sense I won't be doing in this session. I will just make some definitions and be done with it. Maybe in a future session I can do a proof, because I myself am not that familiar with it yet. Alright, okay, so function is like, okay, I will make a function to add two natural numbers. So okay, I made the name. I'm not entirely sure of the syntax, but let's see what happens. So it's a rec, it's like for recursive. It's usually used for making functions. Then I will say given a natural number and another natural number, I will give you yet another natural number. So we have the type. Now we will give a definition. So first the first argument, the first natural number, then another argument, then we will do pattern matching on the first natural number. See, there are two possibilities, right? If it is 0, it will be the second value itself, because 0 is not contributing to the addition. And we have successor of some natural number n, in which case we have to do something a little bit different, I think. First we have make an intermediate value, so I'm calling that intermediate value r, and we do add of the first value and that n, and then finally I will say the successor of r. I'm not sure if this is correct, but let us type check it with Control-C, Control-C. Okay, it is correct. Okay, the reason why all these brackets are needed, these boxes are needed, is because apparently Beluga terms can have computations embedded in it. So we have data and we have computations. So if you want to embed data into computations, we have to use this box syntax. So in this case, we're just embedding the data. We do not really have computations as far as I understand. But all right. So first we have to box it up, the data as a computation, and when we actually need that data, we have to unbox it like this, and then do our business like something like this. Then once we get that data, we box it back up so that we can keep it out. Right. So perhaps I should try some examples, see what happened. Right here. So okay. So what name should I give? Example add 1. Example 1 add. That might be better. Okay. I have 0 and successor of 0. Okay, I wonder if there's a way to actually show. There are ways, but I'm not sure how exactly that's done. But all right. That type check. So perhaps we should try to see how an error looks like. So what if we did not have this box here? Now it will complain. See, that's because successor of R is the data value, but it expects a computation with the data embedded in it. So that's why we need to box it up. So now I reverted it back to the previous state, and now it will compile. Alright. Man, I wish if I knew how to actually show the value of add, but at the moment I don't, so no, we can't, I don't know. Right. Okay, anyway. So that's a nice example for natural numbers. So let's try another one. List. So I do not yet know how to do polymorphic list, and I do not think even that is even possible in Beluga, because I remember reading somewhere that it doesn't have polymorphism in some sense. So let's try with some list of natural numbers. So it doesn't have any built-in types like natural numbers, tuples, or booleans. We have to make them from scratch. So let's say, okay, let's declare the type of list. I'll say list is a type, and there are two ways to make a list. Okay, so one is the empty list, so I'm calling it nil, and the other is add one element to a previously existing list to make a new list. So that's what I mean by cons. So cons will take one list and an element to be appended to it to make another list, a new list. So that's how I define the list type. And let us see if it compiles. Yes, it does compile. Alright, let's try to have some fun with this. So I had two functions in mind. One is the function which is the map function over a list, and the other was finding the length of a list. Both these examples, okay, in fact everything that I have done is actually the first half of the beginner's tutorial of Beluga. I'm just copying from there actually. I just did it by myself. I'm just trying to do it on my own at the moment. So let's try the length function first. So length function is the function which accepts a list and returns the length of that list. So that length of the list should be a natural number in our case. So let's write that function. So I'm naming that function length. So it expects a list and it will give a nap. Okay, let us have the definition. So the argument is a list. Now I will pattern match on that list. So there are two possibilities. One is the empty list and one is cons. So I will write those two cases first. So for data values, we usually use the convention seems to be to use uppercase letters. So I did cons capital N to denote the data value, that nat value, and L for the remaining list. So I made those. So I need to fill these two parts now. So if the list is empty, of course the length is 0. So we'll just put it there. I have to box it in because it's a data value. And if it is cons, it is 1 plus the length of remaining list, that L, capital L, 1 plus length of capital L. So first we need to find, so it's like this, see, successor of and some length of L, something like that. I'll fill that. So first we need to find this length of L. I just put it as a placeholder, don't imitate me. So first we need to compute that. So I will do that. So I will just say I need to make an intermediate step. So first find the length of that capital L. I need to box it in because it's a data value. So having found that R, I can make this. And finally, I guess I have it. Let us try compiling it. Okay, it compiles, it works. So this is the length function. And the next function that I had in mind was the map function. It takes a function which given one particular element of the list, it transforms into another element, another value. So we want to be able to map that function over all the elements of the list so that we get a new list. So in our case, all we have is list of natural numbers, so that function can only be a function which takes a natural number and gives back a natural number. That's all we can do. So let us make that function. So first the function argument, you have to box again, nat to nat. Wait, did I write that correctly? No, I didn't. I have to do it like this. Okay, nat to nat. That's the function, and we have to give a list, and it will give you back. Okay, let me write it here. I have to give back a list. Alright, now I will first have to take the function and the list, and I will have to do pattern match from that list. So like earlier, we had two possibilities, this nil and cons. I'll just copy that. Now we have to fill in these values, right? So if it is an empty list, there is nothing to do. We'll just give it back. There's no values to apply that function to. But if there are values, we have to apply that f on that n. So that means an intermediate step like last time. So we have to first map the remaining values, and then after perhaps we have to give a value to, right? So let's put it here first. FV. I'm not sure I did that correctly. Yeah, it should be like this. Yeah. I have to apply F1 and N to get the V, modify the transform value, and we keep that there. Then we do the same thing for the remaining part of the list. So to get the updated list, I'm storing that in a variable named R, a data variable named R, and then I will piece it together finally. So I have to box again because it's a data value VR, and if I did it correctly, it should compile. Okay, there is some error. Let's see where that is. Oh, I forgot to give the F. Right. Okay, now that works. So even though I do not yet know how to actually show print a given value, let's just see if it type checks at least. So let's see, make an example list of natural numbers, like cons, 0 cons, successor 0. Let us see if that type checks. Oh, that didn't type check. Alright, what did I do wrong? Oh, I should have said that. I should end it right. I guess that was it. Yeah, right. Okay, now let us see if the length function matches. We have length, we have length. Oh, it's a bound program. Oh, that's already a program. Alright. We don't need to box it because it's already a program. Okay, that do type checks, and map. For map, we also need to have a function. I had not thought about that. Okay, let us try making a function then. So, okay, to make a function, we have to do like this. So it's like nat to nat, right? Yeah. So I will make a function which increments, just to do a successor. So I will just do that. That's the easiest, one of the easiest things to do. Of course, apart from giving the same value again. Apart from identity is the next easiest thing to do. So I'm lazy, so I'll just do that. Right, so I have to make the function accept the natural numbers, and I have to do pattern match on it, and I have to consider two possibilities, which are 0 and successor of n. Alright, and if it is 0, I will give successor of 0. I have to box it in. Yeah, I'll give a better name. I'll call it increment. More fitting name, isn't it? Okay, and if it is some n, I guess we will have to do that intermediate step again. I have to calculate some value. I have to do increment of boxed off n in, and then finally I will say successor of R. So I'll comment that out for a moment. Okay, that type checks. Okay, does that work out? Okay, it does work out. Well, that was fun, although I have not done any proofs yet. I hope to do that sometime later. Although I'm not sure when that later will arrive, but so that's it. I hope this is of help to somebody other than me as well. Of course it will be of help to me, but I hope it will be helpful for other people as well. Thank you.